Alright, so what I want to talk about in this video is how to calculate pH of the solution that you're forming during a titration at several different points. Let's have a look at a particular example here. Let's say we have 40 mils of 0.1 molar HNO2. This is nitrous acid, or weak acid. Is titrated with 0.2 molar KOH, it's a strong base. Calculate each of the following: the initial pH before any KOH is added, so just the pH of the acid. Volume required to reach the equivalence point, pH after that, pH at half the equivalence point, and then pH after 40 mils of KOH has been added. Alright, and we also have the Ka of HNO2. We have all the information we need here to calculate all this. It's going to take a little bit of time for us to go through everything, but let's just see what we can do. Usually the first thing you want to do is to always write out the reaction that's happening between the acid and the base. Alright. However, to do part A implies figuring out the pH before that reaction has occurred, so I'm not going to do that yet. And we're just going to say, well, how do we figure out the pH of a weak acid? Well, this is something that we've been through before, and let's see if everybody can remember. There's a particular thing you want to write out when you have a weak acid, and when you're trying to figure out its pH. And okay, my cat has just come and sat all over me. Emma, why is it you sit on everything I'm trying to do? I can't write with your arse on here. Okay, well, I guess you don't care. Alright. If you hear some purring in the background, that's my cat. Okay. She might even say hi at some point. I don't know, maybe. So, yeah, she's kind of purring right now. Anyway, sorry, let me get back to the subject at hand. So, in order to calculate the pH of a weak acid, you've seen this in a previous video, you want to write out the equation that is producing the H3O+. So, in that case, in this situation, I should say, it would be the HNO2. Okay, that's reacting with, whoa, Emma, get lost, dude. I'm trying to write a Q. I can't write a Q with you sticking your whatever all over it. Alright, HNO2 plus H2O produces H3O+, which is what we're looking for if we want the pH, and NO2 minus. Alright. So, we're going to have our initial, we're going to have our change, and we're going to have our equilibrium values. Now, of course, the initial value of our HNO2 is 0.1 molar. The water we're not concerned about, so we'll just forget about that. The initial values of the H3O plus and the NO2 minus are 0 and 0. Okay. When we talk about our change, of course, that's going to be our X, X, and X, and as we've seen before, those have to be plus, and that has to be minus. Alright, so we've got 0.1 minus X, and X, and X. And if we write out our equilibrium expression for this equal to this guy, we know from what we've seen before, when our value of Ka is particularly small, as it is here, we can say that, well, that X compared to the 0.1 is going to be virtually negligible, so we can just effectively push it under the rug. And so we can say then the Ka, which in this case is 4.6 times 10 to the negative 4, is equal to the concentration of the products over the reactants. The products, of course, are X times X, which is X squared. The reactants is 0.1. So that means X squared is equal to 4.6 times 10 to the negative 5. And if you take the square root of that, what you get is something approximating 6.8 times 10 to the negative 3. So that means your equilibrium H3O plus concentration is 6.8 times 10 to the negative 3 molar. So the pH of that acid to begin with is simply the negative log of 6.8 times 10 to the negative 3. Okay? Which turns out to be 2.16. So that is the initial pH of our acid. That is part A done with. Alright, now for parts B through E, we actually have to consider the reaction that is happening between the acid and the strong base. So this reaction is not going to apply anymore. Alright, so the volume required to reach the equivalence point. Alright, now, of course that requires us to remember what the equivalence point means. And the equivalence point is when we have a stoichiometrically equal number of moles of acid and a base. So to do that, we need to know the number of moles of our acid, figure out the number of moles of base, and then figure out the volume of that base. Alright, so we know we have 40 mils of our 0.1 molar nitrous acid. Alright, and we also know we have 0.2 molar KOH. Essentially what we're looking for is what's the volume of that at the equivalence point. So let's just convert this into moles. Now 40 mils in liters, because we're going to have to do that conversion, is 0.04 liters. Okay, everybody happy with that? 0.1 molar means 0.1 moles of HNO2 per liter. Hence why I've got to convert this into liters in the first place. And so what that will give us is 4.00 times 10 to the negative 3 moles of HNO2. Okay. Now in order for us to figure out the moles of KOH, we actually need to know the equation between these two. So let's just write that out. HNO2, that's going to be aqueous, plus, I'm actually going to miss out the K plus because that's not involved in the reaction. So plus OH minus. If this is our acid and that's our base, one of the products we're going to form is water, and the other one is going to be the conjugate base of our acid, NO2 minus. Now, I just want to make sure everybody understands the reason why I've done this. We have a 1-to-1 ratio of our acid to our base. Alright? Meaning that the number of moles of our acid is going to be equal to the number of moles of our base. So therefore, we also need 4.00 times 10 to the minus 3 moles of our OH minus or KOH. But the question doesn't ask us for a number of moles, it asks us for our volume. So we're going to start off with the number of moles that we have. We know we have 4.00 times 10 to the minus 3 moles of KOH. But we also know the molarity of our solution is 0.2 moles per liter. Well, I want to have a volume at the end here in liters, so I'm going to have to put my liters on the top. Alright, I got 1 liter on the top, and that's 0.2 moles of KOH on the bottom. So when I divide 4 to the minus 3 divided by 0.2, alright, what I get is, actually this really should be 0.200, I should make that a little bit more accurate, that should be 0.200 as well. What I get is the volume here of 0.0200 liters of KOH, which if you think about it is 20 mils of KOH. Alright. So that's the volume needed to reach the equivalence point, which actually makes sense because the concentration of the KOH is twice that of the acid. So you should expect if the concentration of this is twice that, then the volume used of this should be half of that volume, which is exactly what it is. Alright, now for part C, figuring out the pH after we've added a certain amount of KOH. Alright, we know that adding in 20 mils of KOH is going to neutralize all the acid. So we know adding 5 mils won't have got there yet. Alright, so our solution is still going to be acidic. Alright, although we've added in a strong base, we haven't added in enough to get rid of all the acid. So the best way to go about a question like this is to construct some sort of table so you can figure out exactly what's present, what's been used up, and what's left after the base has been added. So let me show you what I mean. So this is part C. We have to figure out the pH of our solution after 5 mils of KOH has been added. Okay. So, once again, we want to consider the reaction that's happening here, and it's this one. So I'm just going to write this one out again on the next page. So we know that we have our HNO2 that is reacting with the OH minus. And once again, it's producing the H2O and the NO2 minus. Now there are several different ways how you can label exactly what I'm going to write. Now I'm just going to say it one particular way. I'm going to say here are the numbers of moles of everything we have at the start. We're going to have the numbers of the change in the number of moles, and then the numbers of moles of each species at the end. Alright? We need a number of moles here because this is going to be this is a molar ratio here, so we can't use volumes, we have to use moles. If we use volumes, we wouldn't be able to take into account the different concentrations, and we do have a different concentration here. So that's why we've got to convert everything into moles. Alright? Now, it turns out that we had already calculated the number of moles of HNO2 we had at the start of the reaction. So we're just going to write that here. We started with 4.00 times 10 to the minus 3 moles of our HNO2. Right? We've got to figure out then how many moles of our OH minus we have added in, because right now we don't know that. We know the concentration of the KOH is 0.2 molar, and we know that from what the question said here. So we're going to do a very similar calculation to what we did here. We're going to convert our number of mils of our KOH into liters and then convert that into moles. So, and I'll just write that down here just to try and keep it out of the way. 5 mils is 0.005 liters. Okay, so that's my volume of KOH in liters. That's going to be multiplied by 0.2 moles per liter, and so what I'm going to get here is, this ends up being let me erase that, let me be accurate about this. This ends up being 1.00 times 10 to the minus 3 moles of my KOH. Okay, so that's what I have here, and I'm going to write that here. 1.00 times 10 to the minus 3 moles of that. Of course, the water is nothing, and initially I've got nothing in terms of the NO2 minus because nothing's happened yet. Now, when I look at my change, this is going to react with this. Obviously, this one's present in a smaller amount, so it's all going to get used up. So all of that is going to disappear. Because of the 1-to-1 ratio here, the same amount of my acid is going to be used up. Of course, that's 0, and what this ends up with is 3.00 times 10 to the minus 3 moles of my acid that's left. But bear in mind, when this reacted with this, it formed this. So when I lost 1.0 to the minus 3 moles of my base and my starting acid, I formed that same number of moles of the conjugate base of the acid. So that means I have this. After I've added in that 5 mils of OH minus, all the OH minus is used up because I had more acid. I have this amount of my acid left, and I've formed a certain amount of the conjugate base. Now remember, I have a weak acid, and now I've formed some conjugate base of that weak acid. What have I formed by doing that? I've formed a buffer. Now this is kind of a useful thing for us because you may remember an equation that we can use to calculate the pH of a buffer. Prevents us having to use an ice table. Alright, this is a lot easier, and of course that equation is the Henderson-Hasselbalch equation. pH is pKa plus the log of base concentration over acid concentration. Alright. So all we're going to do is just plug everything in and get out the value for the pH. Now we don't have the pKa, but we do have the Ka of our acid. And if you were to just do the negative log of that, you would get a pKa of that acid of about 3.33. So that means this is going to be 3.33 plus the log of the concentration of base, which is this, over the concentration of acid, which is this. Essentially, it's the log of 1 over 3. And that gives us, this is actually negative 0.48. Alright, so 3.33 minus 0.48 will give us a pH of, what is that? I think that is 2.85. I think that's right. Anyway, that is the pH of our acid, our solution, after we've added in 5 mils of KOH. And the more KOH we add in, the more this pH is going to go up. Notice what the pH was originally. The pH was originally 2.16. After the addition of the 5 mils of KOH, it's gone up. If we add in 10 mils, it go up more. 20 mils, it will go up more, and so on and so on and so on. Alright, next one, part D. In fact, let's just revisit what the question was. pH at the half equivalence point. Okay, now, I'm going to write out the equation again that we're dealing with. So we've got the HNO2 plus OH minus, once again forming the H2O and NO2 minus. Now remember, the half equivalence point means half of the acid has reacted with half of the base. Alright? Now, what that means is, this is the amount of acid that we originally had. 4.00. I'm going to miss off the mole labels here just to save a bit of space. 4.00 times 10 to the minus 3 moles of that. Okay. You remember we said at the half equivalence point, half of the acid has been used up by half of the base. So what that means is, for half of my acid to be used up, I must have used this number of moles of base. Okay? So if we have before, change, and after, my change here is going to be this. So I've used up exactly the same number of moles of my acid. Okay? Because that's 0. This ends up being 2.00 times 10 to the negative 3. And you remember I chose this 2 because that is half of my acid here. Alright? But there's one more important thing here that we haven't filled out yet. Initially this was 0. The fact that these two get used up mean that they form this conjugate base over here. So So that means that I have this like so. Again, all these are moles. Once again, we've been asked to find the pH, so we're going to use the Henderson-Hasselbalch equation again. pH equals pKa, which we said before was 3.33, plus the log of the concentration of base over the concentration of acid. Now this is what's important here. We're at the half equivalence point, so that means the concentration or the number of moles of our acid and its conjugate base are the same. Because they're all in the same volume, those concentrations are the same as well. So that means the concentration of the conjugate base is equal to the concentration of the conjugate acid, which means a log of 1, which of course is 0. So that means the pH is equal to the pKa, so the pH is equal to 3.3. Alright. Now, before I go on to part D, just remember, when I compare this here, after adding in 5 mils, which was this number of moles, I went up to that pH. The half equivalence point, I've added in more moles of that and the pH has gone up again, as you would expect. Like I said before, the pH keeps on going up the more OH minus you add. Okay, now for the last part being part E, which is the pH after 40 mils of KOH has been added. Alright. Once again, we need to know the number of moles of the KOH that we have added, because all we have is a volume. Alright. But once again, I'm going to write out the equation again. It's always important. Alright. Just so you have the access to that table, so it's easy for you to crunch the numbers and know exactly what's happening. So again, H2O plus NO2 minus. So we have our before numbers, we got our change, we have our after. Alright, and as always, the before number of moles for the HNO2 is exactly what it was before, 4.00 times 10 to the negative 3. The difference here is the OH minus, because I'm starting with, it says I'm adding in 40 mils of KOH, so I've got to see how many moles that corresponds to. Well, 40 mils is 0.04 liters. Once again, times that concentration of 0.2 moles per liter, the same concentration we used here, the same concentration that we used here, the same concentration that was given in the question. And what this actually gives us is 0.008 moles, or 8 times 10 to the negative 3. Alright, so this is 8.00 times 10 to the negative 3, and that is 0, same as before. Now here's the thing that's different. Notice when we did part D, the number of moles of acid was higher than the number of moles of base. In part C, the number of moles of acid was higher than the number of moles of base. So there was still acid left and the pH was below 7. In this case, we have gone past the point where we've used up all our acid. So the base becomes the one in excess. So when we think about what's happening here, we've got all this is going to be used up. And we'll be left with nothing of our acid. The same amount of our OH minus is going to be used up. And we are going to be left with that number of moles. But we have our conjugate base that's going to form as well. How much is this going to increase by? Well, it's going to increase by the amount that these two decreased. Plus 4.00 times 10 to the negative 3 moles, so that means afterwards that is the number of moles of our conjugate base. Remember, we're looking for the pH of the solution here. And one thing you should be able to understand is, well, I've added in more base than I had acid, so I should have a pretty high pH. It should be way over 7. But then the question is, well, I have two numbers here. Which one do I use? Do I use both? What do I do? Because I've got a number of moles. I've got to convert these to a volume. But which one do I use? It's actually a simpler answer than you might think. OH minus is a strong base. NO2 minus is a weak base. Therefore, you use the moles of the strong base because it's going to be the one that determines the pH of the solution. So you always want to make sure, if you have a choice of the two, you always go with the concentration or the number of moles of the strong base. So we have a number of moles there, 4.0 to the minus 3 moles of OH minus. But in order to get a concentration, in other words, in order to get this, because in order for us to get H3O plus, we're going to need this. In order for us to get pH, we need H3O plus, which for that we need this. So in order to get the OH minus and concentration, we have the number of moles, but we also need the volume. So let's just go back and see if we can figure that out. Initially, we had 40 mils of our acid, and we added in 40 mils of our KOH. So what's that total volume? Well, of course, that total volume is 80 mils. So what that means is, if that total volume is 80 mils is 0.08 liters, then our concentration is going to be 4.00 times 10 to the negative 3 moles of our OH minus divided by 0.08 liters. All right. And what that gives us is a OH minus ion concentration of 0.05 molar. Now, to get to the pH, there's two different ways we can do it. We can calculate the H3O plus, or we can calculate the POH and get the pH from that. I'm just going to calculate the POH. The POH, of course, is the negative log of the OH minus. So in this case, that is negative log of 0.05, which is 1.30. And if you remember, the pH of any solution can be found from this equation. Alright, so therefore the pH is 14 minus the POH, which in this case is 1.30, giving us a pH of 12.7. And as we said before, because I've added in a lot more strong base than I had weak acid, the pH is going to be way over 7, which it actually is. So what we've done overall, I know this is kind of long, what we've done is calculate the pH of our solution at 4 different times and figured out the volume to reach the equivalence point. Alright, you can do exactly the same sort of calculation with a strong acid and strong base. It's just not quite as complex as what we've been doing here. Anyway, that's it. Thank you.